Hello everyone, welcome to Practical Mechanics. I'm Mohsen. Today video we learn how to calculate combined stresses in a shaft that is subjected to transverse shear force, bending moment, twisting moment, and axial load. Let's start with an example. Consider a shaft with circular radius 2 inch is fixed at one end and transverse shear force 150 pound applied to the free end and a torque 4200 pound inch and an axial load 4000 pound applied in the x direction. Just pull the shaft. In this case, because of the transverse shear force load, bending moment also is applied to the shaft. And if you draw the bending moment diagram, it is maximum at the fixed end. Maximum at the fixed end. Then bending moment diagram is like that. 150 times the length of the shaft, assume 20 inch, is minus 3000 pound inch M. And you will see from the free end of the shaft till the end of the shaft, it changes linearly, and maximum happen in the fixed end. Pull or tensile load is the same as in all cross section 4000. Torque also is the same as for all cross section till base is the same. And transverse shear force load also is the same for all cross section. Then, because bending moment is maximum at the end, this makes this cross section at the end the critical cross sections. We wanted to calculate the stresses at this critical cross section. The other cross section doesn't matter because the stress on them is less. And in design, you must consider the worst case scenario when stresses are maximum. Okay, let's start with bending moment. And before that, we need to calculate area and I and J. This is the properties of the cross section of the shaft, and actually area is 12.56 inches square. I is 12.13 inch to the power 4, and J is 25.13, and this one is 25.57 I. Then, after calculation of the properties of the cross sections, stress at V actually called 3 points A, B on the neutral axis, C, and D. These points, you can consider them at the fixed end as well. A means the point that is on top, C on the bottom flange, B and D are on neutral axis. Okay. Sigma bending maximum, we are looking for maximum, not any other stresses, because it must be a max, C max, divided by I. M is 3000, doesn't matter negative or positive. We consider the absolute value times C, which is 2 inches, and I, which is 12.57, and is equal to 477.3 psi. That's bending stress. And sigma normal stress due to axial load, which is always the same, equal to P over A, is equal to 4000 divided by 12.56, and is equal to 318 psi. That's these are two normal stresses. And top surface, top point actually experienced the tensile normal stress, and bottom surface for bending experience the compression stress, but for axial load, all points experience the tensile normal stress. Okay, these two can combine together. Before we combine together, let's calculate the shear stress due to transverse shear force load and torque as well. Let's consider first the shear stress due to torque. Tau is equal to torque Tc over J. Tau max happen at the outer surface of the shaft. Torque is 14,200, C is the radius 2, and J is 25.13, and the value is equal to 334 psi. And tau max due to transverse shear force, which produces horizontal shear stress. We call it horizontal shear stress, but it is in all directions, on the cross sections and on the horizontal layer of the beam, the same at any point. Then, this is maximum. We are looking for max. Then is equal to when V is max, then Q is max, and then divide by I, doesn't change, and B is this point at the sections that width of the cross sections at the point that you are looking for horizontal shear stress. If, for example, the cross section is circular, if you are looking for tau of horizontal shear stress at this level, then B is this width. If you are looking at this level, B is this. And if you are looking at this level, but we are looking for tau max. Tau max for horizontal shear stress of occur at neutral axis. Then we consider it at neutral axis. And then we cut the cross section at neutral axis. And this Q for this cut section is equal to A times Y bar. Y bar is the centroid of the semicircle from neutral axis, which is equal to, for radius, divided by 3 pi. That's the distance of semicircle from its Q. If you calculate the area 12.56 and multiply by 4 times 2 divided by 3 pi, you reach the value 5.333 inch cube. That's Q that you need to calculate here. And that's the Q max actually. If you cut at any other sections, top or bottom, the neutral axis is not Q max. Q max only at neutral axis. What about V max? Because the transverse shear load doesn't change. If you draw the shear force diagram, you have a diagram like this. Constant from the free end to the end and is equal to 150. Then, but if for example, we have a V diagram that is like this, for example, actually never reach to zero at the support. If it is a simply supported beam, then you was looking for Vmax, maybe this one, maybe this one, from the V shear force diagram. But here shear force diagram is a straight horizontal line, and V for all cross sections of the beam is the same. Then, if you put the value 150 times 5.33 divided by I 12.57 times V, V here is this diameter 4 inches. You reach to the value for tau 15.9 psi. Then we have two shear stresses and two normal stresses. Combine normal with normal and shear to shear. Let's combine normal to normal. First normal is axial. At point A is 318. At point C also 318. At point B also is 318. At point D also 318. All of them are tensile. Plus bending. At point A, it equal to 477.3. That's the neutral axis here. Compressive 477.3. And then changes linearly with respect to axis. If you add them together, you add them at point to point. For example, point A for axial to point A for, because it's the same place that the stresses happen for bending. And how much is it if I wanted to choose the resultant? I can get rid of this calculation here. Then 380 added 477, it is 795 psi. At here, the value of bending is 0, and at the bottom point C, we have this, which is negative, plus 3118, which we reach to 159. If you add them together, connect them together, you will see neutral axis now is here. Because what? Because of this value added to this one and make it 0. When P over A from previous neutral axis, the centroid of the cross section becomes down Y. How much is Y? M times Y divided by I must be equal to P over A. This stress here at this point must be equal to P over A. In order to this point became the neutral axis, stress will be 0 at this point. Then the distribution of normal stress in the cross section of the beam is like that. Tensile and compressive. Okay? Then that's the combination of normal stresses, axial and bending, added together. Okay? Then what about shear stresses? Shear stresses, don't forget 15.9, horizontal shear stress. 15.9 happens at what? I draw the full cross sections because the shear stress is at cross sections. Here is 15.9. Plus. And 0 at top and 0 at the bottom. Plus. Due to torque, shear stress due to torque, due to direction of torque here, the shear stress is 334. And here at A, at B also, this direction 334, at C 334, at A, 334. Always is tangent to the cross sections, to the outside surface. For example, if you draw it here, it should be in this direction. And distribution is like that. If it is a solid shaft, it changes and reaches to maximum at the outside surface. This is why when a shaft is only under torque, pure torque, they make it hollow because the center of the shaft doesn't carry too much stress. There is no need to put the meat of the metal of the shaft in the core. They make it a core hollow shaft. Okay, when we added them together, see what we have. At the cross section, here is 0, here is 34. Okay, at A, we have 334. Here is 50.9 plus 334. We get the largest value, which is equal to, actually, if we can do it, 350 psi. And here it's the same because V equilibrium is 0, here is 334. And here they subtract from each other. 334 minus 50.9 is 318. Then, what is the critical point at this design? Point A for normal stress and point B for shear stress. Okay? Then, we have to point that we can study the combination of stress, normal stress and shear stress at that point. At point A, we have normal 795 and shear 334. If I wanted to show both in a three-dimensional case, I can use here in this video, I just write down this value of stress in order to draw the Mohr circle in the next video. Okay, let's show them all of them together. All stresses. This is the shaft. At one of the cross section close to the fixed end, because the fixed end is the maximum tensile stress happen at the fixed end. Here you have a normal 795 and you have a shear 334. Tau sigma. They are normal together. This is tangent to the surface, and this is normal to the surface. At B, we have only 150, 318 normal, and torque 400, torque is 334. Torque is added together, 350. Of shear stress added here. And at C, we have a compressive stress 159 and torque is not in the same direction. Let's show it different. Torque is in this direction, 334, and normal, how much? 159 sigma. at D, torque is 334 minus actually 150.9 is equal to 334. 318 addition minus 50.9. And then normal stress is the same. Normal stress at this point is the same as 318 because bending stress at neutral axis will be zero. That added nothing to this one. Then this is the case that happened inside the material. And which one is more critical, has more shear stress and more normal stress? One of them is this point A. This is point C. And also you will see that this one is not actually a little tau shear is larger, but a considerable amount is less in normal stress is less. Then the critical point for this design is A. And if we wanted to know how these two stresses, 795 and 334, combine together, we must use Mohs circle to find out the combination of what's the result of combination of these two stresses, shear and normal at point A. And we reach to another stress, which is called principal stresses, maximum normal stress that can happen inside the material. And we use the normal stresses to find, we have two normal stresses, maximum and minimum. And also we can find maximum shear stress inside the material, which is not this value, 350. No, larger than this. In the next video, we draw more circle, and you will see how this shear and normal stress combine together and give us a new state of stress inside the material. Thank you for watching, and see you in the next video.